Hi everyone, and thanks for participating in this talk. During the presentation, I will talk about the risk associated with IoT devices, and in particular, I will share my personal research on security cameras. And before we even start, I would like to briefly introduce myself. I'm Pietro Oliva, and that's my Twitter handle. I currently work as a security researcher, as Matteo said, and I previously worked also for Sony, JP Morgan, SEC Group, PwC, and GMV in a variety of different security roles, which include also red teaming, penetration testing, and security audit. Now, let's talk about the agenda. What are we going to see during the course of this talk? So, first of all, why would they even perform research on a camera? What's interesting about it? Then the next thing will be talking about what's been done before. So what was the information available to me before even starting? And then once I figured out what was done before, then I put myself into a challenge that we'll see very soon. And then I will describe what are all the steps that I took to achieve success in this challenge. And then I will talk briefly about what are the lessons learned and possible future work on these cameras and conclusions and Q&A. So let's get started. Why would they even perform security research on a camera? Well, the starting point was that many people just say, oh, these devices are not secure. And I say, okay, that's fair enough, but I want to verify these claims by myself. And I was also looking for a challenge and a learning opportunity. So I thought this will tick all the boxes for me to start looking into it. So let's talk about the previous work. Once I bought this camera, I get out of the store, and the first thing I do is to Google this NC200 camera, and I find this vulnerability from March 2016, and it's a command injection affecting these two cameras, NC200 and NC220. Now, this was already patched on the latest firmware version, so it's not very exciting. And I also thought, is there really only one vulnerability affecting this camera? Is it possible that they made it so well that this is the only thing that I can find on the internet? So that's when I started putting myself into a challenge. And the challenge was to hack the latest and greatest firmware image. And I wanted to do it in a special way because remember, I was trying to get something out of it. I wanted the learning experience, not just hacking it by any means. So I started from the hardware because I wanted to learn a bit of hardware and how to dump the flash and all these things. So I dumped the flash and performing reverse engineering, so deliberately excluding fuzzing and black box sort of test. And the interesting thing was that this also different architecture than what I was used to. So this was a good opportunity for me to learn some MIPS. And some other interesting constraint I put myself was to use some tool that was free and open source. So everyone could replicate my steps without having to afford any expensive reverse engineering tool license and anything like that. And something that I could use basically everywhere because I like a lot to do some hacking on the go. So without any sort of preparation, like I found that there is this tool called Radar that I'm sure most of you know. That is a reverse engineering tool that can basically run almost everywhere, including on a mobile phone. So hardware analysis and flash dumping. How did I start? So the first thing that I did was to literally just take pictures of the main board of the camera, which you can see here at the bottom. And also search on Google this picture. And the way I found it was, you see this FCC sort of logo. This is basically a standard for electronic devices. And they all have this ID that if you search it online on the official website of the FCC, which is an organization that controls radiation emission from electronic devices, you can find all the documentation and internal pictures of the electronics that they basically index. And this was very useful in my case because I didn't have to, for example, open this metal shield in order to see what was inside. And I could clearly see that there was this processor and this RAM. Now, without this, I would probably have to remove this and probably risking to break my device. So it was really handy for me to find that. Now, apart from that, this is great. We know the processor and the RAM, but we need to know more. So I started literally just searching all these labels. These components will just have IDs that you can search on the internet, and you will find data sheets, very likely, if they're not something really unknown or really custom. So what I figured out was that there were these two flash memories that are SPI, speak the SPI protocol, and I dumped them. So that was the initial step. Now, once I figured out that we had this flash, how did I dump them? I mean, what was the process that I took? So I used the bus pirate. You can use any other tools, but it's just the tool that I had at hand at the moment. So what it does, it's this board that you can see in the background of the slide. And basically, it gives you a serial port on your laptop. You connect it via USB, and it gives you a serial port that interfaces automatically with all the SPI chips, or even I2C, or it speaks a range of protocols, and you can just use it as a proxy to talk to your devices. And in order to do that, I use the flash ROM, which is basically a tool that automates these commands that you send over serial. So instead of me manually typing every command to dump basically blocks of bytes one at a time, I just use a tool that automates that process. So it will do that correctly without any sort of problems. And I figured out finally that the 8 megabyte flash contained the main firmware. So we got lucky. Let's see now what we do with this. So once we get this raw image, it's just in a raw format. You need to do some tooling to kind of extract it and further analyze it. So in my case, I used binwalk plus Jefferson for file system extraction. Basically, it's just scanning signatures until it finds, for example, the Jefferson file system, and then it invokes Jefferson to do the file system extraction itself. And as I mentioned before, I decided to use Radar as the main reverse engineering tool. And I picked one target, which is one of the most critical binary in this firmware, which is the binary called IP camera. This is basically handling all the HTTP requests going to the FCGIs. Now let's talk about some vulnerabilities that I found using this technique. The first one is, as you can read, it's a null pointer to reference. And this is a login function. It's a function that gets called when you perform login on the web interface of the camera. And as you can see here, I will walk you briefly through the code. You have two arguments, username and password, which are user controlled. They go to this match password method that just checks your config file for your password. And if it's incorrect, it just keeps the entire block and will give you some authentication failure message. Otherwise, it goes ahead. And the first thing it does once the authentication is successful is to check what is your browser. So it takes the HTTP user agent header, and then it takes iPointer to this string and passes it to str because it wants to check if your browser is Firefox. So as you may have noticed, there is this arg58, which is argument 0. It's basically the pointer that comes from HTTP getenv. Now, the problem is that this will normally work until you remove the user agent header. Because if you remove it, then this method will return a null pointer, and then you're going to have a null pointer reference right here when you call str. So because of this bug, basically, when you trigger it, all the web interface goes down because you cannot do anything without this binary running. So this was the first bug. And of course, as a result of this bug, I started the vulnerability disclosure process with TP-Link. So I put a list of stages to kind of show what is the pain of this process, just to show how long it takes to get something fixed. So I started reporting it on the 4th of December, 2019. And the answer I got from TP-Link was, yeah, the camera is not supported anymore. So basically kind of, we don't care. I said, okay, fine. So I left it there for a bit, and then I said, you know what? I'm going to see if other cameras are affected. So maybe they're not unsupported, and they will be forced to fix it. And after a short time, I realized that all of the NC series cameras were affected by the same vulnerability. And after warning them, they didn't take any action. And I decided after almost 4 months to drop it as a 0-day. And magically, after roughly a week, they fixed it. So they needed a little extra push to find the motivation to fix the vulnerabilities. And they fixed it in all the cameras. And starting from there, they started taking the reports and deadlines much more seriously. And in the end, I promised that I wouldn't report any more issues as a result of them asking me, can you please confirm this is the last issue you report, because we have released 2 firmware updates in the past 2 months. So I said, okay, fine. Okay, let's talk about the next bug now. This is a Stack Overflow. What is this about? So we have this feature that is called delete multi-user method. And what it does is exactly what it says. It deletes multiple users. The way it does it is basically creates a wrapper to this delete user method and basically goes in a loop. And in this loop, it takes the usernames and just deletes them. It's a comma-separated list of usernames. Now, the way it does it is it deletes the user and then takes the error code and it puts it into a string that is stored on the stack. And then this string is then concatenated in an array that is again on the stack. It's basically a concatenation of error codes from all the deletion operation, right? The thing is, if you look closely at this loop, it will basically go until the next comma is found, and it will just, if it's 0, it means that there is no next comma, so it just breaks the loop. Otherwise, it will keep looping. As you may have noticed, basically, we control the number of iterations, and we are storing effectively, we are concatenating strings on the stack in this FP plus 40 because of this str cut. So this means we control the number of iterations and we are storing things on the stack. We are concatenating. So this buffer gets bigger and bigger and bigger until you basically overwrite the stack. So this will, of course, crash the process because it's a Stack Overflow. And initially it might sound exciting, but it isn't too much because the only thing that we really partially control is the error code. And it's very, let's say, unlikely that we will find a combination of error codes that will allow you to obtain arbitrary code execution. So we classify this as a denial of service. And if you were wondering what the proof of concept looks like, it's just something that you can fit in a tweet. It's just literally usernames equal a bunch of commas, and that is enough to crash the IP camera process, which is ridiculous. Now, the next bug is an according encryption key. So there is nothing really too complex in here. We can see that there is this p backup file, there is this TP link, and there is an e backup, and then there is a call to desencrypt. Okay, so we know everything. We know there is a desencryption algorithm. We know that there is a plain backup and an encrypted backup, and there is a TP link, which is probably the encryption key. Now, it looks straightforward, right? But we still have a problem to solve. We know the algorithm and the encryption key, fine. And I was able to find a tool that will correctly decrypt these configuration files. And I will get random data if instead I used any sort of standard DES implementation. And I could understand why. And I was thinking I was doing something wrong until I realized that you don't simply use an encryption key. And this is what I figured out. After basically checking all this code, which by the way is hosted on GitHub, this Vico and me, this random guy, and I compared it with the standard DES implementation, which you can find some information about in Wikipedia. If you look at this initial permutation table and start comparing these constants, you will figure out that they just changed 1 unit in every single value of this. So this is the reason why I will never, ever be able to decrypt these configuration files with any standard test, because they literally changed all the constants. This is just one because there isn't enough space on this slide to show all of the tables that they changed, but they basically changed all of them. So this is a kind of funny thought process that they had. They could just use a strong encryption algorithm, but they decided instead to customize a weak encryption algorithm. So effectively creating a security by obscurity situation. But of course, we managed to solve the mystery. So now we know everything, and we can decrypt backup files, and we can figure out the structure of these backup files. So this is what it looks like in a NC200 camera. It might be slightly different for others, but the concept is the same. So what they have is just a small header, which has a magic, the total file size, and the MD5. Then some null terminated string that says fingerprint. It's just hard-coded. There is nothing special about it. And then some padding. And then after the small header, you will find the file entries. The file entries are very simple. There are like 4 bytes for the absolute offset of the file content. So they have this list of files at the beginning, and then at the end, they have the contents. And then the file side, some 0 padding, and then the null terminated file name plus padding. And that's it. That's what the format looks like. So before we go into the demo, thinking about this, what we have in this configuration file, we have file paths, right? We have paths and contents. So I think this can give us arbitrary file override. So let's see how that works in practice in this demo. So I prepared this little script, 1.sh. All it does is creates a config for the NC200 camera, and it includes this demo1 and demo2 HTML files, and it's going to upload them in user local www. And then after that, it just encrypts them using the NC200 key, and it's going to output this all demos CFG file, which is basically the encrypted configuration file. Now we're just going to the web interface, and we're going to restore this backup file, which is called all demos CFG. Restore. Now this is going to take a while because it's going to reboot the device, because usually it will just reboot because you need to, I don't know, change some service configuration that needs to be restarted. So they didn't want to go through the pain of figuring out if your changes require a restart or not. So they just decided to just reboot the entire device. So all the services will just restart and everything will hopefully be fine. Right, so hopefully the camera should be back relatively soon. All right, here we go. So the first demo I want to show you is demo 1. Right, cool. So what did I do in here? What I did was to just replace this camera frame with a very well-known game called Doom. This is just an example, right? It could be anything really. It's just to show that you can really do anything you like, because you will basically overwrite files as root. So you have all the privileges to write anything anywhere. This is not very useful apart from my simple demo. Now I want to show you something a bit more useful. So if you notice this tip, you need to install a camera plugin in order to be able to watch the stream of your camera. Now I found this ridiculous in 2020, and I decided to do something about it. So I made demo 2. And after you authenticate, effectively, you can see this is my hand. You can see the live stream without having to install any plugins. Now let's go back to the presentation. Okay, this is the next bug. It's about a new command injection. So this command injection, before we even start, you may have noticed that this is a screenshot from my mobile phone. This is very interesting because this is something that, this is what I was talking about. This is proving that you can find security bugs while you are bored, maybe don't know, in a long travel in a plane where you have no internet connection, you have nothing to do, and you just decide that you're going to find a vulnerability, and maybe you find it. That's what I did, and that's what happened. So let's start from the CM command. The CM command is a wrapper to system, so it's just executing commands. And if we go backwards to figure out what are the arguments, we figure out that it is this echo %s. So it's echoing something to somewhere. And we can see that we have this encrypt key, which is something that we control as the user in a HTTP request. And then we see this TMP encrypt key. So we know what's happening, right? It's echoing this encryption key that you are providing, and then it's storing them in some encrypt key folder. And then it just executes the command. Now, as you may have noticed, there is absolutely no check anywhere about this particular encryption key. So you can effectively inject shell meta characters and get arbitrary command execution. This is great, but it only affects NC260 and then C450 cameras. It's only a feature that exists there. So let's see if we can do something better on that. And that's when we talk about this Bonjour command injection. So this Bonjour service, the way it's started is like this. We can see this CM command again, so it's a good sign. We know that we are executing stuff. And then we see these arguments that are like MDNS responder POSIX, and then it's passing this %s. Now this %s is going to be this A1, argument 1, which comes from V0. V0 comes from this Bonjour. So what's going on here? So we are basically getting the name, right, of this device, and then from some configuration file, then we are putting it into V0, and then we are passing it to CM command. So we are building this MDNS responder POSIX. Our injected command is going to be here, and then everything will be okay for us. We can execute code, right? But there is something that we need to take into account. So there is, before you can even set an alias, there is this product alias check that gets executed right before. And if you look at this method, there is nothing really special going on, except for this strlen call with this alias string that we control. So all it's doing is making sure that you don't provide a string that is greater than this 0x81. Otherwise, everything will be fine. Now, this is true for all cameras, except for the NC210, where basically this check is done properly and you cannot just set a new alias. So you need to figure out a way to set an alias and then exploit this vulnerability. And in order to do that, I will combine the previous vulnerability, the hardcode encryption key, to get arbitrary file write. So I write the new device name, and then I will use this command injection to take the command from that device name. And this must have been the logic of the developers. You cannot inject command if you check for long strings. That's something that they probably thought. So this is a bug that I call one bug to rule them all, because it affects all the DMC cameras. It can be triggered very easily, and it gives us reliable root shell without any problem. Let's see if that's true in the demo. Right, so let's go to demo 2. All right. So as I said, I was going to combine two different vulnerabilities for the NC210. So I want to demonstrate that. I have this system.conf, that is where the product name is stored. And as you can see, as a product name, I'm putting this. It's basically a command injection. What I'm doing is setting some executable, and then some file to executable, sorry, and then just executing it. Now in this to-do.sh, what am I doing? I'm generating a payload with Metasploit, which is going to be our payload that is going to be executed. And then I'm creating a config for this camera, and I'm going to upload it in system.conf. And the next thing I'm going to do is to add this payload.elf in this etc/s, and just encrypting this configuration file, because the camera needs an encrypted configuration file to work. So let's run it. Now this will start automatically the MSF console. So in the meantime, we go here to the web interface. And and we just upload the configuration file in the Docker file. So this is a bit slow because it's running on QEMU. So demos 2, right, systemconf cfg restore. Now this is going to reboot the camera again, and it's going to take a while because it's in QEMU. So I will go in the meantime to demo 3. In demo 3, what I want to show you is the command injection in the simple version, which is basically without combining it with the arbitrary file write. So all I did was to make this m0leCon module that exploits the bonjour command injection that I showed you before. And it's just setting some very simple parameters like the remote host, the port, the target, username and password for the web interface, the payload, just a standard m0leCon payload, and then when you want to receive the shell, basically. So this is the NC200 version. So I'm going to run this on the physical device that I have. And this is another camera, which is the NC450 that I'm running in QEMU as well. So let's run both of them, and let's see if we manage to get a shell on both of them. All right, cool. It looks like we have a shell here. Yes. And as we can see, we're running as root, and we can see here our wonderful command injection, and it's running as root. And we are in this user local spin directory. Now, if we check the other camera, it's the same thing. So we are basically executing all of this wonderful command line. And we are in the same folder. And we got a shell in both devices with the same exploit. So this works on all the cameras, right? But I just put a couple just for as an example. Okay, it looks like the other camera rebooted. So we're going back to demo 2. Now I want to show you what happens as soon as we start the HTTP server. So this is the start SH. It's just a helper that I built myself because usually we'll have the HTTP server starting automatically, but it's all emulated, so I have to do it myself. So once the HTTP server starts, it will just start the bonjour service. And as you can see, we got a shell in here. Cool. Let's continue. Let's talk about lessons learned now. What did we learn out of this experience? We learned that code reuse means you're going to have the same vulnerabilities across different devices. And this is apparently more often the case than initially thought. So don't exclude ever that what you find in one product only applies to that product. Always cross-check, and you'll find some surprises. Something else that I wanted to reinforce is that dropping a 0 day after a fixed deadline has been passed can get the vendor to fix the issues. Because maybe the vendor doesn't really understand and is not very keen to patch the issues. So if you give them enough time and they still ignore you, and you warn them and they still don't understand, they don't want to patch things, then I don't think it's a bad idea to drop a 0 day. And something that I wanted to reinforce is that reverse engineering can reveal bugs that are hard to find, or in some cases even impossible to find via fuzzing or black box testing. For example, the bonjour command injection was very unlikely to be found via black box testing. That's also probably why it was not discovered before. And the reason why is that the interface didn't really suggest that you could even change the device name anywhere. So if you didn't know about the set sysname.fcgi URL, you will never know that probably. And it will be kind of hard to guess. Now, if you like this kind of research and you want to keep working on it, because I probably won't, because I won't report any more bugs as I promised, I have a few ideas to get you started. So you can look for vulnerabilities that can be exploited from the cloud. So it's even more interesting because you don't even need to be in the same Wi-Fi network or hope that somebody has misconfigured the network to allow you to access their camera from the internet. Something that is also interesting is to look for vulnerabilities in the browser plugin, because I'm sure judging by the code quality I've seen until now, that is going to expose an interesting attack surface in your browser. And then something else that you could do is to definitely look for vulnerabilities in the mobile app, which is available, I think, for Android and iOS. And the fourth step that I suggest, if you want to look into these things, is to look for baseband vulnerabilities. So imagine if you could just get a shell on these things by just being in the same Wi-Fi range without even being connected to the network. Now let's talk about the conclusions. We can definitely say there was more than one vulnerability on the NC cameras. And you don't need any expensive tools or anything special, any preparation to find those issues. You can find them on a plane while you are traveling, when you're bored and you don't have anything to do. And reversing is necessary if you want to find bugs that are hard to find via fuzzing or black box testing. So make sure you complement your test. And I can say for sure that it was a good idea to never use my camera for any actual real camera purposes, but just for research fun. And now I can say from experience that indeed some IoT devices are insecure. Not all of them. I mean, I can't talk for all of the devices, but I can say the devices I looked at are not secure enough. And something that is really important, and I wanted to make sure I delivered this message, is that we have a shared responsibilities. Security researcher and vendors have a shared responsibility at making these things more secure. So it's not just about us finding the bugs or about them trying to make things secure by themselves, but it's the collaboration between these parties that allow things to be more secure. And that's it. Thank you for listening. If you have any questions, just make sure to write them in the chat.
Thank you, Pietro. And so it is pretty early, so maybe we'll do a longer break. But we have some questions from the chat.
Yeah.
So Max asks if it was hard to emulate the firmware on QEMU.
So it was not hard. If you try to use, for example, the firmware analysis toolkit, which I did try, is supposed to give you a wonderful script that does everything for you and just spawns QEMU. But for me, it didn't work. So I found it easier to actually take a random QEMU image, like a Debian image, and just basically install the files that I needed from the camera. And I had to patch the IP camera binary because there was some error related to some hardware that was missing. Something about the network. Of course, I didn't have any real physical network devices or any Wi-Fi at all in the QEMU image, right? So some things are likely to fail. It really depends on the device you are looking at and the firmware it's running. So that is the way that I decided to approach it, and it did work. I hope that answered the question.
Thank you. And we have a non-technical question that is if the TP-Link has a bug bounty program. I mean, the direct question is if they pay for vulnerabilities, but I think the main question if they have a bug bounty program.
So the answer is I have no idea. So, so I invite you to search for this program. I mean, it's very good to do research and find these things, have some fun with it and learning experience. But if you can monetize your efforts, it's even better, right? I mean, I didn't even think about that when I started my research. And so I wasn't just interested, so I didn't look for it. But I invite you to do so if you want to get something out of it, some bounty. Definitely possible if they have it.
Okay, thank you. Another question, Pietro asks if you could provide some ways to use these vulnerabilities during one red teaming activities. Sorry.
So as I showed before, the Metasploit module I forgot to mention that actually. Thanks for reminding me. The Metasploit module is publicly available. It's on GitHub of the official Metasploit framework repository. So you can just git clone and get my module to exploit these cameras. And I will also release at the end of this conference a standalone Python script. If you're not very keen on using Metasploit, you can just quickly test it with your Python script. I hope that answered the question.
Thank you. Last question is, if you report a bug from Michele, if you report a bug to a vendor and this company doesn't give an answer, can you publish it on GitHub?
I don't think you can do that straight away. I mean, you will have to give them the opportunity to fix things. So you only record to, it should be a last resort, right? Dropping a 0-day. You should never do that unless there is really no hope that these guys will fix anything. So if you feel that's the case, usually the standard deadline is 3-4 months. So if after that they still don't patch anything, even though they are aware of it, then I think it's time to consider disclosing a 0-day.